Hello, I am Charlotte Lee, a graduate student working with Dr. Bowling. Today, I would like to talk with you about climate change and agricultural water management. Learning objectives include explaining how climate change may influence agricultural water resources here in the Midwest, identifying agricultural water management strategies used in excessively wet or dry conditions, and describing how drainage water recycling could help Midwest agriculture become more resilient to climate change. First, let's review the difference between weather and climate. Weather represents changes in atmospheric conditions at a particular location on the scale of hours, days, or months. When you check the weather in the morning, you are preparing for these short-term conditions such as a thunderstorm, a blizzard, or a cold snap. This graph shows the hourly change in temperature on the y-axis over 5 days. You can see a diurnal cycle in temperature. Climate, on the other hand, represents changes in atmospheric conditions over a larger spatial and temporal scale, such as years to decades. Events such as El Niño, which is related to periods of warmer ocean temperatures in the equatorial Pacific, can influence climate variability at this scale. Even though you can see variation in the daily temperature in blue, over 5 years, the average daily temperature in red follows an annual cycle where temperatures are warmer in the summer months and cooler in the winter months. This example is from Australia in the southern hemisphere. That is why the warmest temperatures are around January. When we discuss climate change, we are discussing trends in climate patterns over decades or centuries. For example, this figure shows the change in annual temperature over 6 decades. We need many years of observation to get this big picture perspective. Here we have examples of annual average precipitation on the left and maximum temperature on the right for the lower 48 states. These values represent average conditions over a period of 30 years. The left image is from 1961 through 1990, and the right image is 1971 through 2000. These reference climate normals are recalculated every couple years because over time there are changes in climate. What are some causes for climate variability? There are multiple causes behind climate variability and change. These include variations in Earth's tilt and orbit around the Sun, solar radiation outputs, plate tectonics, volcanism, which can add gases and particles to the atmosphere, changes in sea surface temperatures such as El Niño Southern Oscillation, and human activities. You've likely heard of the greenhouse effect, which is a naturally occurring phenomenon where naturally occurring gases such as water vapor, carbon dioxide, methane, and nitrous oxide trap heat in the atmosphere. Without it, life could not be sustained on Earth, because average global temperature would be about -20 degrees Fahrenheit instead of 55 degrees Fahrenheit. However, human activities such as combustion of fossil fuels can increase the concentration of greenhouse gases. In 2018, the EPA estimated the percent of all U.S. greenhouse gas emissions attributed to human activities was 81% for carbon dioxide, 10% for methane, and 7% for nitrous oxide. Fluorinated gases do not occur naturally in the atmosphere and are entirely introduced by human activity. Higher concentration of these gases in the atmosphere enhance the insulation like a blanket. This effect is sometimes referred to as global warming. There are different signals that can be observed in Earth's atmosphere, oceans, and surface that can indicate long-term changes in climate patterns. You have likely heard in recent years about decreases in polar sea ice and glaciers and increases in sea levels. Let's look at changes in near-surface air temperatures. Over the last 2,000 years, we see variation in Earth's temperatures. We observe an increase in global temperatures over the last century, sharply rising over the last couple decades. Temperature changes are projected to become even greater over the next 100 years. This means we can no longer be able to rely on much of the historical climate data. Many sectors, including agriculture, will have to prepare for changes in temperature and precipitation to come. Here is an example of projected annual temperature and precipitation changes for the Midwest. The greatest temperature changes are projected for the most northern portions of the region. It is important to note that even as the amount of annual precipitation is projected to increase, the timing of when that precipitation is occurring and evapotranspiration demand from vegetation will also be shifting. How do we expect climate change to impact agriculture in this region? Here are some potential changes. Wetter, warmer winter and spring conditions could bring an increase in soil moisture and subsurface drainage. Wetter conditions can delay planting or stress crop roots and would drive the need to increase the intensity of drainage in fields. Increasing temperatures and accumulation of growing degree days could increase the growing season and be favorable for crop yields. However, increases in nighttime temperatures can reduce crop yields, and the decrease in the number of chilling hours can negatively impact fruit tree yields as well. During the growing season, precipitation events are expected to be spread further apart, which could lead to periods of water deficit stress during critical growth stages, when evapotranspiration is high. Precipitation events are projected to become more intense, which could increase agricultural runoff and erosion, decreasing water quality downstream. With more extreme events, we can expect more crop stress, damage, and loss. There are also other influences such as increasing plant disease and pests, and influences of humidity and carbon dioxide fertilization on crop growth. These are beyond the scope of this presentation. Historically, the three most common weather-induced crop losses in the region are excess moisture, freezing, and drought. Between 1989 and 2015, producers of specialty crops such as sweet corn and popcorn claimed $130 million in crop loss due to wet conditions. You may remember the cool, wet conditions of last spring, which set a record-breaking amount of acres to be claimed under the Prevent Plan. This shows that managing excess water stress will continue to be important in the Midwest in the face of climate change. Here you can see an example of observed agricultural drainage at two different sites in the Midwest. Even though both sites have approximately 400 millimeters of annual drainage, you can see when the drainage comes is distributed differently. The site in Iowa, on the left, receives most of its drainage during the growing season, in May and June. While in Indiana, on the right, the majority of drainage occurs during the non-growing season, December through April. How might drainage change across the region in the future? These simulations project that most of the region will experience up to a 10% increase in non-growing season drainage. Northern Iowa and Minnesota have greater projected increases as the depth of soil frost, which historically prevented water from moving through the soil in this season, becomes less intense with warming winter conditions. This figure integrates multiple portions of the water balance. It shows average difference between water supply, precipitation, and water demand, potential evapotranspiration, during the late growing season from July to August of 1981 to 2010. This figure tells a more nuanced story about water availability than an annual or seasonal precipitation map. Here, areas with darker brown colors have higher potential moisture deficits and could benefit from supplemental irrigation during this portion of the growing season. Understanding how climate influences drainflow and how distributions in precipitation and evapotranspiration may change in the future can help influence the methods we use to manage agricultural water resources, as our goal is to improve the resilience of farms and provide environmental benefits such as reduced nutrient loading downstream. For example, if you live in a region where a low fraction of drainage occurs in the non-growing season, you would not want to select a management method that targets managing water during that period. If you are in an area that is at risk for water deficit in the growing season, you may need to manage for both wet spring conditions and dry periods in the summer. Earlier in the semester, you talked about subsurface drainage. There are several different management strategies that can be used to help increase water storage and decrease the amount of water and nutrients leaving a field. Controlled drainage increases water storage in the soil profile of the field. Saturated buffers increase the water storage in the buffers surrounding the field. And we're going to focus on drainage water recycling, which is a practice that captures drainage water in a pond so that it can be used to provide supplemental irrigation to crops during dry periods later in the growing season. Drainage water recycling, or DWR, provides a source for supplemental irrigation. Here you can see simulations showing historic and future non-irrigated corn yields in gray circles for the West Central Crop Reporting District in Indiana, which has rain-fed agriculture. Purdue University is located in this crop reporting district. Crop yield is on the y-axis and the year is on the x-axis. Here we can see blue triangles, which represent simulated irrigated corn yields for the same region. You can see how providing irrigation can reduce the year-to-year variability in crop yield and can significantly reduce the crop loss during severe drought years such as 1988 and 2012. We can simulate the impact of increasing the storage of a drainage water recycling pond on stream flow. This hydrograph shows several different scenarios, from conventional or no drainage pond in dark blue to a drainage pond that is 6% of the cropland in light green. You can see that as storage increases, the peak simulated stream flow decreases when there is enough capacity in the pond to retain water. So in January 2010, there was enough capacity to retain water, and so we see a decrease over half in the peak stream flow, compared to in late June, during this specific event, there was not enough capacity to hold water, and so it made little to no difference on the stream flow. Overall, with increasing pond size, we can reduce the mean annual flood. It is important to note that the annual outflow of the pond is only reduced around 3% with increasing pond size. So ponds are not preventing water from leaving the fields as much as they are increasing the residence time of the water in the landscape. Increased residence time can allow more time for potential plant uptake or processing of nutrients. How does drainage water recycling impact downstream nutrient loads? Over a 16-year period, we can see that DWR has a large reduction in nitrate loads and a smaller reduction in soluble reactive phosphorus, or SRP. This reflects nutrient processing due to wetland vegetation and microbes in this simulation. A pond without vegetation would be expected to have lower nutrient reductions. So you can see how DWR is a practice that not only helps increase the resilience of the agricultural system by providing a source for irrigation, it also provides environmental benefits by reducing peak stream flow for small events and increasing residence time and the potential for nutrient processing. In summary, climate change will shift the annual volume and timing of precipitation, which may or may not align with evapotranspiration demands of crops across the region. Drainage water management strategies can give farmers more control of the water table in their fields to remove excess moisture for planting, but also to store soil moisture on site in the soil profile or a pond for crops to use later in the growing season. Drainage water recycling could help farmers enhance crop yields with supplemental irrigation during dry periods, while also providing environmental benefits from increasing residence time and nutrient processing.